and welcome to this EMTP-RV webinar study from A to Z. My name is Henry, and I have the pleasure today to demonstrate how to use the Transient software EMTP-RV version 3.0 to conduct a Transient Recovery Voltage study. Just a quick reminder, the recovery voltage is the voltage at the terminal of a breaker after an interruption of the current. We here focus on the transient, which means for frequencies higher than the power frequency. When the current is interrupted, another voltage can occur across the breaker, which can challenge its interruption capability. The latter, once open, has to be able to withstand the maximum voltage at its terminal, but not only. Since the breaker does not open instantaneously, while it is opening, it has to be able to withstand the fast-growing voltage across its terminal. The standard IEC 62271.100 gives the rating envelope of the voltage withstand for a circuit breaker above 1000 volts while it is opening. The goal of the engineer is to make sure that the TRV resulting of a breaker opening, so-called inherent TRV, caused by any event that can occur in the network, stay in the rating envelope, also called rating TRV. For that, the application guide IEEE C37.011 identifies the two events that are the most challenging for the breakers. The first one is an interruption of the current following a three-phase to ground fault at the terminal of a station. This event will produce the highest overvoltage. The second one is following a short line fault of a single phase to ground fault. The TRV in that case will be the one with the highest rate of increase of the recovery voltage. In the end, the engineers will have to make sure that the TRVs of those two events do not reach the rating TRV. The application guide IEEE C37.011 provides an example where both terminal fault and short line fault inherent TRVs are calculated. In this webinar, I will reproduce this example with EMTP, which use exact model to find the TRV, and we'll compare these with the standards. But before that, let me introduce EMTP-RV to the one of you that are non-user. First, few words about PowerSys. We are the company that commercialize EMTP-RV and mainly deal with the following points: the business development, the sales management, the pre-sales and after-sales front office support, the training, the technical support, and the development. We also offer some engineering services for the simulation on this slide: the voltage regulation, the power transfer capacity, the voltage stability, the fault recovery, the switching, the short circuit, the lightning, and harmonics. Please contact us if interested at sales@powersyssolution.com. Here are where we are located around the world. So now let's talk about EMTP-RV itself. So EMTP-RV is a transient software. What is a transient software exactly? A transient software starts with the same equation as a stability package. For example, for an inductance, it will be the voltage. It's equal to the derivative of the flux. But instead of going to the Laplace world, the transient software will integrate this equation step by step, because one of the assumptions in Laplace is that the model is valid only for the fundamental frequency, whereas for a transient software you don't do any assumption. Of course, the number of time steps have to be smaller than a frequency than in the frequency domain. So here are the main kinds of simulation we can use EMTP-RV for. Let's start with the network solution, for example. In this study, the input would be all the power constraints of a network. For example, the load, which can be PV or PQ, the machine that can produce as well, that the production can be set as a power for a certain voltage, PV or PQ, and the slack bus. Knowing all these constraints on your network, the software run a load flow simulation and find in the end the voltage everywhere on the network, the angle of the voltage, the power, the current, etc. So it's not known. EMTP-RV is more known for having being a transient software, but its load flow capabilities are actually huge. They can be unbalanced. We stay in the phase, so it can be multi-phase or single phase, and it's actually more and more used in distribution companies just for its load flow capabilities. So then we can do a classic short circuit study, but since it's a transient software, you have access to the transient current and the waveform of the steady state current as well, where you can see the DC component and the high frequency content. Then we do some insolation coordination in case of lightning, for example, or all type of switching, the capacitor bank switching, the TOV, TRV, etc. Phase resonance can be studied as well. A lot of customers use EMTP for phase resonance, where you can change a lot of initial conditions like the flux, the initial flux in the transformer, and study like that, all kind of influence. Then we do also more powerful study, for example, in the grid converter or the renewable energy that are power electronics. So in that case, we study every single switching cell with the saturation in the IGBT, the control, the protection. So it gets a very big model, and it's actually extremely precise to simulate a network like that. And that's what now, for all the renewable energy or the power electronics, the only approach that is very valid, it's with the transient software. Also, since we have access to the waveform that are supposed to be the same as in the grid, it makes it possible to study the power quality. So for that, we have some tool to calculate the RMS value, the harmonics, the THD, and all kind of power quality indicators. And it makes it very precise because all the saturation in the network are considered. Also, we can do some transient stability. For that, we have a library of AVR and the governor. And it's in the end, instead of running a simulation of less than a second, you will run a simulation of few seconds or minutes to study the reaction of the control. Finally, something new in the software that will be released this year, the protection tool. In EMTP, we are convinced that transient software are the most powerful software to study protection, because we can reproduce the saturation in the CVT, the phase resonance area of the CVT, the saturation in the CT, and then in the relay model we built, we reproduce each step, the burden resistance of the relay, then the anti-alias filter, the sampling, the DFT to extract the phasor, and then we reproduce all the logic from the manufacturer instruction manual to make it very close to the reality. So this tool will be available this year. So in the end, if you open the software and you go in the simulation options, that's the type of simulation you have. The load flow, we talked about this one. The steady state, which is also a static study, but here we consider all the frequency model of the device. So the Laplace model. And we will solve the network for all frequency present in it, and then superimpose the result together. Then we have the time domain simulation, which is the one used for transient, integrated step by step. Then we have two other kind of simulation, very convenient. The first one is the frequency scan. So we use such a study, for example, if you want to study the connection of a power plant to a network, and you know this power plant might inject some harmonic, then you do a frequency scan at the point of connection to identify all the natural frequency of the network. So in the end, the output of this study is the magnitude of the impedance and the angle of the impedance for a large range of frequencies at the point of connection. And you identify like that the pole and the zero, and you make sure the harmonic injected are not close to one of them. The last one, the statistical study, it is used to reproduce the mechanical behavior of a breaker. Since a breaker is a mechanical device, it cannot open and close instantaneously. And there is actually a difference between the theoretical closing time and the real closing time because of the mechanical behavior. So for that, the manufacturer provides some statistical law that can conduct the behavior of the breaker for the closing or the opening around the mean value. So in EMTP-RV, what we do is we have in the input, you can see the mean time, the mean closing time, and the statistical law that dictate the behavior of the breaker. Then we're going to run a lot of simulation. It can be hundreds or 500 simulation. And between each simulation, the switching time of each pole of the breaker will change a little bit following the statistical law. And you can identify like that the worst overvoltage and make sure to design the coordination, the insulation coordination properly. Here are the range of frequency we can study with the EMTP-RV. It's in the end all the frequency that are present in a network. Let's start with the high frequency, like the lightning, for example, or the switching transient. For such frequency, the parameters of the line and the cable, for example, change. They are not the same anymore that at the fundamental. For example, because of the skin effect, the value of the resistance will increase. Same thing, the inductance, the value of the inductance will change as well with the frequency. So in the EMTP-RV, we have some frequency-dependent model of line to reproduce that. With this model, the parameter change during the time domain simulation with the frequency. They are very powerful model. Also, this model reproduces the propagation of the waveform through the line. Let's take, for example, a line of 200 kilometers. If you energize the line at the end, nothing will happen at the other end. When the energization is done, there's going to be a waveform that travels through the line, reflect at the end and come back. And they're going to be like that, a back and forth of the waveform that's going to be damped eventually by the resistance. So in the EMTP-RV, we can reproduce all that with the model of line. And actually this behavior has a big influence in the overvoltage. We can also simulate slowly a phenomenon, like I talked about the temporary already, but also the DC in case of HVDC or a wind turbine, for example. So when you buy EMTP-RV, in the end that's what you get. The computational engine that runs the calculation, the graphical user interface, where you can build a network, put the devices together, connect them, enter the data in the mask. To open the mask of a device, you just double-click on it. And then you have Scope View. Scope View is a tool to display the waveform or to do some post-processing, like you can put in PU, in RMS, use FFT to identify the harmonics, study the power quality, etc. We also have another tool to look at the waveform. It's mplot, which is very convenient for statistical study, for example. So here are the benefits of EMTP-RV compared to other transient software. First, it's a very robust simulation engine in terms of the way it solves the iteration, the non-linearity. So for that, we do some iteration to find where we are on the curve in case where you have IGBT, which are nonlinear, or some surge arrestor, or all kind of saturation. We do iteration to find exactly where we are on the curve within a time step. Also, we use sparse matrix to solve the network. That makes a big difference as soon as you have a large network, because the length of the simulation, so the simulation time, and the memory usage to run the simulation increase as an exponent 3 of the size of the network. And so you are very limited if you don't use sparse matrix as soon as you have a big network. Also, we have an automatic initialization of the time domain simulation. That's very convenient because most of the time for the machine, for example, or even the slack, you have the information of the power, the voltage, the angle of the angle of the voltage, for example, for the slack, but you have no idea what is the angle of the rotor at t equals 0 to initialize your network. So in EMTP, you set all the power constraints, you run the load flow, and then during the steady state solution, the power angle of each machine on the network is initialized. So the position at t equals 0 is found. Also, the voltage to apply on the field of the machine is calculated as well. So it makes it very easy to just start the simulation and everything is initialized. There is no initial transient. Also, EMTP-RV is very convenient to customize and script. All the graphical user interface is based on JavaScript, and so you can write a script that change all kind of scenario, exclude or include device, add some device, replace them. You can do parametric study while you run a simulation, save the result, change the parameters, run the simulation again, and do like that parametric study. Also, you can create your own device, so you can write a code. You have access to functions that call the inputs and set the outputs of the model, and you can integrate your model in the network. You can also import a model from Simulink, for example, or for ETAP. So when you open EMTP-RV, that's what you do. First, you create a new blank case, for example. You drag and drop the device from the library, you put them together and enter the data. Then with this network, you can run all types of simulation. For the first two, the multi-phase load flow and the steady state, the result comes out in two ways. It can be as a tab, where you have the name of every node, buses, devices with the voltage, the phasor of the voltage, the power, reactive power, the current. So it can be a very large tab in yen. The second option is to display directly the result on the graphical user interface. So that is way more convenient and easy to visualize. Then for the time domain simulation, obviously we cannot save every single signal. The memory usage would be terrible. So for that, you have to set scope before running the simulation. For that, two options. You can double click on a device, and there is a tab named Scope, where you have a list of signals that you can choose to scope. Or we have a meter library, where you can find voltage scope, current scope, sequence voltage or current scope, power, etc. And you can connect directly this scope on the design like you would do on your network directly. It's really a software in the loop. Also, I talked about those advanced model of line. Obviously, not every user is supposed to know how to set them. So that's why in EMTP we have some devices that help you to create the model. Let's take the example of the line. If you go in the line library, you're going to have the frequency-dependent model of line, and you're going to have a device named line data. In this device line data, you're going to enter all the data commonly provided by the manufacturer. The example of a line, it will be the number of conductor per phase, the size of the conductor, the DC resistance, the length of the line, and then automatically in this tool you're going to generate the file. The file will be saved by default at the same location of the design. Then you just have to go in the frequency dependent model of line, and you have an option to load the file, and then your model is all set. So we use such an approach for the frequency dependent model for the line, the wideband model for the cable, the surge arrestor, and some advanced model of transformer like the BC trend, for example. Here are a list of references that use EMTP-RV. So now I'm going to open EMTP-RV and demonstrate the study of today. Okay, so now we're going to start with the study of today. So we're going to build this network, which is from the application guide IEEE C37.011. So it's a pretty interesting case because here you can identify several types of TRV. So we study the TRV in a substation. So you know, it's always difficult to know the scope of the study, where we should stop modeling, where we should stop the model. So the advice for that is, so you have to model the substation and the line going out of it until the next discontinuity. For example, here a transformer, or then here we separate in two lines. So you have to represent those lines going out of the substation. If it's connected directly to a transformer, then because of the big impedance of the transformer, it's enough. So that's you know, with the experience it's come, but that's some advice we can give. So here in this guide, they provide some end calculation for the TRV, and so it will be interesting. We'll try to compare the result given by EMTP-RV, which use very powerful model to reproduce the propagation in the line and to calculate the TRV in the end with the end calculation of the application guide. And we'll see that in the end the EMTP-RV follow this standard and respect it, and can give even a more precise result after if you build more strong model. So as the first step, we will build this model using the same approximation, so that the parameters are constant, as we can see here. So first we'll use constant parameter model of line and not frequency dependent. Also, as you can see here, only the inductance are considered. In our case, we will consider also 1% of resistance, you know, because it's to avoid all kind of numerical problem. It's not a good idea to not consider the resistance when we cut a current. So here we'll put 1% of resistance to be more realistic. So then once this network will be built, we're gonna simulate it and have a look at the inherent TRV for the terminal fault first, the breaker 1 and the breaker 3. So here the configuration of the breaker, all the white breaker here, they are closed during all the simulation, so we'll not reproduce them. The breaker 4 is open. The breaker 1 and 2 and 3 open during the simulation, but as you can see here we have a loop when the breakers are closed, and mathematically the software doesn't like that, so we will not reproduce the breaker 2, only the breaker 1 and 3, as is it here in the end. So we're going to open the breaker 1 and 3 at 20 milliseconds for the breaker 1 and at 30 milliseconds for the breaker 3, and have a look at the TRV at those breakers. So that will be the first step. So we'll see that at the breaker 1 we'll have an exponential TRV because of several lines in parallel. The breaker 3 we're going to have an oscillatory TRV because of the transformer here, where we cut the current directly at the secondary of the transformer. So we will see all that with the EMTP and compare the results with the standard. After that, we will build using the control library. We will build a device that draws the rating TRV according to the IEEE 60,271 100 standard. So we'll build this device and we'll be able to compare directly with the EMTP the inherent TRV with the rating TRV. So the rating TRV is the one the breaker has to respect, and so we'll make sure that the TRV produced here stay inside the envelope of the rating TRV. So for that, we will choose a breaker which has a certain short circuit current interruption capability, and we'll do the comparison. So all that first for the terminal fault, and after we'll do the same thing for the short line fault. I remind you again, the terminal fault is used to identify the worst overvoltage, the short line fault, the worst rate of increase of the voltage. And to finish, I will do the same case but with frequency dependent model of line. We will see that here we are pessimistic because we use the parameters that are valid only at 60 Hz. After we use frequency dependent model of line, and for high frequency the inductance and resistance change, and in the end it's less pessimistic than the case here. Okay, so let's start now by building this network. So I will build it following that and add in 1% of resistance. So let's open EMTP-RV. It can take some time to open. Here we go. So first we're going to open a new blank case. So for that you click on new. You just have to wait the software finish loaded here. Okay, so it's a new design, a default design. So first thing, I have to save it in a location here in this folder, webinar TRV. You cannot run a simulation if the design is not saved yet. So here it will be the terminal fault. Okay, so if we have a look at what we're going to build, right here. So we have 1, 2, 3, 4, 5, 6 Thevenin equivalent. So the Thevenin equivalent, you can find them in the library sources, the AC voltage source, and impedance. So to find the voltage of the impedance of those Thevenin equivalents, you can use the short circuit current or power of the network. And so like that you can find the impedance. Also, if you have the single short circuit current or power, you can find the zero sequence as well. So here the voltage is 362, it's balanced, 362 kilovolt line. The inductance is 16.2 at the primary, and I had 1% of resistance. Okay, so for this one here, it's a 15 kilovolts. So after they're going to be a step-up transformer, 15 kilovolt line to line, and at the primary of the transformer, the inductance is 0.209. And so the resistance 1%. Yes, good. Here it is. Oh, here I have one missing. Okay, so you have done these two here. So now I'm gonna do the last four, which are here. So they are all 145 kV. And the inductance of the first one is 2. And the resistance is 1% of that. This one, the inductance is infinite because of the transformer. So we put a very big value for the inductance. Okay, so that is the same thing as an infinite one. And let's put a big value as well for the resistance. Okay, then here we have an inductance of 16 ohm. And so here 0.016. There you go. And for the last one, the inductance is 22. So it is. Okay, so then here we have to model the auto transformer and the step-up transformer. So usually for the auto transformer we use a 3-winding transformer, but in this case no many data are given, so we cannot really build this model here. But again, only the sequence inductance is considered here, so it's exactly the same thing to use a 2-winding transformer, which is in EMTP the 3-phase nameplate. So we'll just use this one. So it's connected in YG. It's a 200 megavar, 200 MVA. Sorry, here a 362 to 145, and it was a 9.26%. And so here I take 1% of that. Okay, can connect it here. Same thing with this one, but this one is a delta Y, grounded again. It's a 150. 15 kilovolt to 145, and it's 5.5%. Here it is. Okay, so then the line you can find them in the library lines. So as I said, first I'm going to start with a constant parameter model of line, and as a next step a frequency dependent model of line. But you can find all of them in the library lines. So all the lines are the same type, only the length is different. So I'm going to build the first one and copy and paste it. So considering the input you have, you can choose here if you have the resistance, inductance, capacitance, you can fill this one. In that case we have both. So we're gonna fill the one with the resistance, the surge and the surge impedance, and the propagation speed. Okay, so the length of the first line is 44. Okay, so again we put a small value of resistance. Same thing for the zero sequence. So here you have the mode. The mode 0 is the zero sequence. The mode 1 is the positive sequence. So in that case we do a 3-phase to ground fault. So the zero sequence doesn't matter really, but let's feel it still. Here's the zero sequence surge impedance, and here's the positive one and the speed. So for the positive sequence it's about the speed of light. So after considering the length of the line, that's how you can determine the time step to use for the simulation. It's in the end, to have an idea, you can see the shortest line, which is this one, 16. So it will be you have to choose a time step considering the time for the waveform to travel through this line and reflect, and of course you should like put several time steps to simulate that. So in the end you can find like that the suitable time step for the simulation. Or another option is just to start with a typical one, for example 1 micro for such a study, and look at the waveform after if they are not, if the results are not segmented too much. But it's always better to know before running the simulation what you expect to have. And it's actually why this guide where we reproduced this example from is very good, because it gives a way to find before running the simulation to know what's going to happen. Okay, so now let's draw the bus of where the fault will occur. So for that I go in Home, Draw Signal, Draw 3-phase bus, and I draw the bus here. Okay. Okay, so then the standard to reproduce the breaker during a TRV, the standard specify to take an ideal switch. So an ideal breaker is the model to take to do TRV. Then in EMTP we have more advanced model. If you want to be even more precise, we have model that reproduce the pre-strike and the reignition, or even the arc model. So we can get very precise. Of course, obviously after that you need more parameters to set those models. But again, if the goal is to respect the standard specifies to take an ideal switch. Okay, so here is the model of the ideal switch. Let's call this breaker 1. So it's closed in steady state, and it open, I said, at 30 milliseconds. I copy and paste it, and that's breaker 2. So to change the name, you just have to double click on the pink string, which is the name, and you write the new name. Okay. Right. Okay. Okay, so it is. I built this network, so let's compare quickly. So you can see the length of the line appears in gray, so it's a quick check. It's possible to do a quick check. So see, when I open the breaker 3, the transformer is isolated. When I open the breaker 1, all the rest, we consider the breaker 2 open all the time, as well as the 4, and the other to be closed all the time. Right, so that's how it is. So then let's model the faults. So in EMTP we model the fault with switches. So for example, you close a switch to the ground to make a fault directly to the ground. You can close only 1 pole, 2 poles, 3 poles, and you can connect 1 pole to another to do a line-to-line fault. So you are completely free. You can also add a resistance to simulate a fault with resistance. So yeah, it's you can model all type of fault, balance and balance. Then the ground you can find it in several libraries. For example, in sources you can find it. You drag and drop it here. So then I open the mask of the fault, and I make it close in steady state and never open. So see, when you say close in steady state, it puts a negative value, and never open, it puts automatically a very high value. Okay, so now my circuit is built. So the first thing the thing we have to do now is to specify what value we want to look at after we run the simulation. So here our goal, as I said, as a first step, is to identify the inherent TRV. So it's in the end, in the guide, the IEEE application guide, they provide a way to calculate that by hand. It can take some time. So here it's we do it by simulation, right? So you double click on the switch, you go in the tab scope, and you select the voltage. And we do that for the 2 switch. Actually, this switch is supposed to open at 20 milliseconds. Okay, and so like that, we will have the inherent voltage, TRV. Okay, so let's run this simulation. So first, I have to set the simulation. So I go in the tab Simulate, Simulation Options. So as I said, I can keep 1 microsecond, and I'll see after if the results are good. And let's simulate 60 milliseconds. The second breaker open at 30 milliseconds, so that we can have time to see the worst overvoltage. Here I didn't change the angle of the source. It doesn't really matter in the end, because since here we have a fall to the ground, the angle of the source doesn't matter. Actually, I left 0 because the application guide doesn't give any information about that. In EMTP-RV, you have some capabilities to use the load flow to initialize all those voltage sources considering the power and the reactive power they generate. So you can initialize them like that. But here it doesn't really matter, especially because the frequency following the TRV are way faster than the power frequency. But again, in a study, it's better to initialize them with their power constraints. Okay, so let's run the simulation. So then we're going to have a look at the results using our tool ScopeView. So we have 2 tools to look at the results, ScopeView and Hemplot. So here we're just going to use ScopeView. So it takes a few seconds to open. It's a good tool because you can do a lot of post-processing on the results. Okay, so here when I click, so we are in the signal type branch voltage. When I click on the signal type, you can see breaker 1, A, B, and C. So that's the first breaker, the voltage. And we can do the same for the breaker 2. I'm going to put it in another page. So I change the page here. And I click on play. So that's here the TRV of the breaker 2. We can superimpose the TRV. Here it is. And we can zoom on it. So see here we can see the phase B open first. So according to the standard, excuse me. Yeah, no, never mind. So yeah, here the breaker phase B open first. And so now let's have a look at here. Okay, so that's the inherent TRV. But here actually we forgot one thing which has a big influence. And actually we forgot it in purpose because we're going to see the difference on the breaker 1. When we do a TRV study, it's always good to, it's actually not always good, we have to model the stray capacitance. It's very important, and you'll see it actually have a pretty big influence on the results. So for that, the standard, the IEC standard, or even the IEEE, they are harmonized now. They can give some tab of typical value for the stray capacitance of the equipment in a substation. So if we can have a look, for example, here for this substation, here are the equipment we have and the value after. Okay, and the total is 6.5 nanofarad. So I'm gonna have this stray capacitance for the substation, and we'll have a look at the difference so that you can understand how important it is. Okay, so I'm gonna add the stray capacitance here at the at this side of the breaker in the end. This thing is useless. And ground it. So I said it's 6.56 nanofarad. So the tab I show you was for it was the equipment in the size of the line and the transformer, but there is another one at this side of the transformer. Okay, and this one is 3.228 nanofarad. We can put a name, for example, C stray kappa or C stray auto transfo. Okay, here, I don't know, C stray substation. It's always good to give a name to the device so that it's easier for people to read after the design. Okay, so let's run the same simulation and have a look of the difference. The difference for the transformer will be visible. Here we were cutting a current of an inductive transformer, which is really inductive. So we cut the current instantaneously. That's not very physical. That's why we have those spikes, and we don't find those oscillatory behavior the standard was mentioned. But now, if I edit C, we can see this behavior. If I zoom on it, we have the behavior, the oscillatory behavior of that, and it gives actually a very bad stress on the TRV, and so for that the standard gives some solution to avoid those stress by adding capacitance, for example, but that's not the purpose of this webinar. Okay, and so here is the inherent TRV of the line side in the substation. So like that, you can identify the worst overvoltage. Again, you can use, for example, the 2-point cursor here to identify the mean and the max value. You can put in PU. It's very easy. You just have to here you go in the signal and you can divide by a base. We won't do it here. Okay, so that's the first step of the study, how to find the inherent TRV for the terminal fault. So after, we'll do the same for the short line fault, but before, I would like to build with you a way to draw directly the rating TRV, so the TRV which is linked to the breaker to the in EMTP. Okay, so for that, I'm gonna choose a breaker, right? So for example, I will use the standard. So I will take a breaker which has 30 kiloampere of maximum current interruption. And if I then use this standard, I can find like that, I can draw this TRV capability related to this breaker. So the first step is to know what test duty to use. So for that, I'm gonna look at the current in steady state through the fault. Then if the current through the fault is 100% of this value, I'll have to use the one on this, the parameter of this line. If it's 60%, I have to use the one of this line, 30%, 10%, etc. For 10 and 30%, we have an envelope which has only one slope, and it's a 2-parameter envelope. For the 60 and the 100, it's a 4-parameter envelope, as shown in this graph. If you are between those values, the standard can tell how to do interpolation between them. Okay, so let's have a look at the current through the steady state short circuit current through the switch. Let's name it fault. So for that, I go in the simulation option, output, and I click on printed output option, steady state and load flow. And I specify that I want the voltage and current in RMS, because here it was the RMS value. I run the simulation again. At the end of the simulation, as you will see, we have here a button that opens a steady state web. It opens it on HTML. It's an HTML page. So then if you click, let me zoom so that you can see better. If I click on transmitted power, then you have here the power and the current through every device of your network in steady state. So before we run the time domain simulation. So then I can use Ctrl plus F, the Windows shortcut, to find the device faults. And we can see we have 17,200 amps of faults, right? 0.17 exponent 5. Okay, so 17. So here we can see we are roughly at T60, right? 17 divided by 30, it's about to be T60. So here to go faster, I will use directly the parameters of the T60 study. So we're going to build in EMTP a device. As soon as the fault happens, it will draw this curve, and we're gonna superimpose this curve with the voltage, the inherent TRV we just found. Okay, so for that I'm gonna open a new case. I'm gonna build it in a separate design. There you go. So again, I save it. I'm gonna call it rating TRV. Okay, so what I'm gonna do is I'm gonna put this device in a sub-circuit, right? So that it will be easy to copy and paste it. So to build a sub-circuit, I go in Option, and first I have to define the input and output of this sub-circuit. Oops, sorry. So I click in New Port, and I choose the input. So the input will be the state of the breaker. So I can call that state breaker. And I click on Place. Then the output, the first output will be the TRV. But as you see in this TRV, we have actually two parts. We have one which is delay a little bit, so we're going to reproduce this one as well. So actually I can copy and paste this one and change the name, because they are both output. Okay, so when the breaker is open, its state value go from 1 to 0. So what we're going to do is we're going to integrate this time to have the time which is the x-axis of the curve I showed before. Okay, so now we're going to use the control library. So here I have 0 as soon as the breaker open. So then what I'm going to do, if I want to integrate it, I will transform it as a 1. So for that I will use a not. So I take the device name function of u, select function, and I say not. Okay, so now input here I have 1 as soon as the breaker open. So I can take an integral here, and so now I have the time of the time as soon as it open. We count the time here. And so now if I want to, what I'm going to do is I'm going to put a function that give the slope, the slope of this curve, and we're going to integrate this slope considering the time to find the TRV. Okay, so for that I take another function here. So I'm going to define then in the mask two values of the TRV, of the rate of increase, two values for the rate of increase. And I'm going to call them RRRV and RRRV1 and RRRV2. The input of this function name is U1. Okay, so as soon as U1 is bigger than 0, and U1 is U1 in minuscule, and U1 is smaller or equal to a variable that will be specified in the mask name T1, sorry. Then the value will be RRRV1. So here what I said is, here I have a condition. As soon as this condition is true, the value is 1. If this condition is not true, the value is 0. Same thing here. And so in the end, when both those conditions are true, the value will be the slope RRRV1. T1, if you want to have a look, T1 is the first value here. And RRRV1 will be the value given here in kilovolts per microsecond. So then for the second, I can go to the line, it doesn't matter. For the second slope, we'll have it when U1 is bigger than T1. And U1, sorry, is smaller and equal to T2. In that case, we will multiply. We'll multiply by RRRV2. So as soon as I want to transmit a variable from the mask to the subcircuit, I have to put hashtag like that. I have to put the variable between hashtag. I will show you after how to create the mask. We are doing it right now. So the first step is to build what happened inside the subcircuit, right? And to put the variable inside, and then we're going to mask all that and create the subcircuit and mask it. And in the mask, we will have to define T1, T2, RRRV1, RRRV2. Okay, and so now I just have to integrate this signal. The limit here will be, so now when I integrate that, I draw the curve actually. And the limit will be UC here, and after it will be straight. So I can put the limit here. Even if after I'm going to integrate 0, it's not necessary, but just to make sure, let's put the limit. So it's the high limit. So we'll have to define UC. So that was for the main part of the TRV. Now if I want to model the small delay, I can just do the exact same thing. I can copy and paste this one, and but this time instead of starting at 0, it will start at TD. Okay, TD is this value here. So instead of integrating straight away, I wait TD and then I integrate the same slope. And this one will stop at a time named T prime. Here it is. You can actually display what you write if you want to verify. For that, you right click on the device, go on attributes and model data. So now you can have a look at what you write inside to verify. Okay, and again I integrate this one, so I copy and paste to go faster. Okay, so now what happened is we're gonna integrate that, and after it will be flat. Actually, if we don't want it to be flat, if we don't need to go back to 0, we can reset it as soon as we reach T prime. Right, so let's do that. But it's easy, we just here we say as soon as so we remove the first part and we say as soon as U1 is higher than T prime, the exit of that will be 1, and we put run to the reset control RC. If you open that, you can see RC is the reset control, and we're gonna put that to 0. So actually for 0 you can take the constant here, connect it, and say 0. Okay, so here it is. We just built the control that's gonna draw that. For the future, if you want to use this control, you can send me an email and I can send it to you. Actually, that will be integrated in the EMTP version, the commercial version, very soon. So then to create the subcircuit, you just stay in the tab Options and you click on Create Subcircuit. Then you can use, for example, the quick subcircuit, put a name, TRV rating, 4 parameters. Okay, let's call it TRV rating. And this is it. Then you can change the drawing, for example. So for that, sorry, I went a little bit fast. You right click on it, go to Edit Symbol, and you can like that edit the symbol. It's very convenient. And call it TRV rating. Whoop. Okay, so let's test quickly this device to make sure it works. So for that, I'm just gonna put a signal generator at the input that's gonna reproduce the state of the breaker. So we will start, it will be a state. We will start at 1, the breaker is closed. Then we put an amplitude of -1. So that means we'll go to 0, the breaker is closed. That will go forever. And we will do that at 10 milliseconds. Okay. And let's scope the output. So the scope we find in the library meters, control signal scope. And we can scope both of them. We have TRV, I changed the name of the scope, TRV_D and TRV. Okay, so let's see if we build that. Oh, I forgot something, we're gonna have an error message. I'm sorry, I forgot to create the mask, because we have to define all these variables now. So to create the mask, that's actually a big part, I forgot. To create the mask, you go in subcircuit info, then mask, and you click on mask the subcircuit. So I remind you, I have to define the constant T1, T2, T prime, TD for the delay, RRRV1 and RRRV2. And all those information are from the standard here. So it's in the line T60. So in the end, I'm just gonna copy those. Okay, so let's do it. So now I mask the circuit. If I double click on it, it opens this box. So I can define here the variable and then write the name of the one I want to transmit. I can also apply some calculation in this box, so it's very convenient. Okay, so here we can put commentary to say what we do. So that's define the variable defined by IEC standard, right? So the first one is UC. Okay, so the breaker we use is let me see, 145. Okay, excuse me. T60, sorry, you see it's 231. I knew I did mistake, it's 231. Okay, so then U1 was 115. Okay, so I just write all those parameters here Okay, U1 it's 150, so I write them directly. Okay, T1 is 38. As a commentary I can say it's microsecond. Here it's kilovolts. Kilovolt line to ground. Then T2 it's 228 microsecond. TD it's 5 microseconds, so it's very small, 5 microsecond. So that means the time step has to be smaller than 5 microsecond at least. Then you have U prime, which is, as a reminder, the value here of the delayed TRV, which is 58 kilovolts. Then T prime, which is 28 microsecond, and rate of increase of the voltage of the recovery voltage, which is 3 kilovolts per microsecond. Okay, so here see I put convenient value, but then they have to be put in a standard value. So for example, you see I multiply by 1000, same thing for U1. Okay, same thing for T1. Here we put it in second. Same thing for T2. Same thing for TD. Oh, here I did a small mistake. Then U prime. T prime. So T prime, it's the time for the delay TRV. So then RRV1, so it's the first rate of recovery voltage, rate of increase of the recovery voltage. So it's directly equal to the one specified by the standard. So it's in kilovolts per microsecond. Then RRV2 is the second slope for the TRV. So it's in the end equal to UC minus U1 divided by T2 minus T1. Okay, it's, if I show you the curve, it's the slope here. And after, so we integrate first this one and then this one to find the TRV. Okay, so then I have to write here all the variable I want to transmit to the subcircuit. So there was UC, T1, T2, TD, T prime, U prime, RRV1 and RRV2. Okay, so now when I press to OK, this script will be will run and we'll know if we have an error. Here we don't have any error. We can check the result we have. Again, we go in attributes, model data, visible. So we can see here the result of the variable we transmit and have a look if they are good or not. For example, T prime, it's way too big, so I probably did a mistake on it. Yes, it's not multiplied by that, it's multiplied by, it's a microsecond. Okay, so now the rest looks alright. Let me check. Oh, we are missing U1 as well. We have to give U1. Okay, then now we're gonna run the simulation. If, for example, one variable is not defined here, which is inside the subcircuit, we're going to have an error message. If the simulation run, that means everything is well. So it's okay, the simulation run. We can quickly have a look at the TRV with mplot. So we view scope with mplot. We can draw them. Okay, so at 10 microseconds, the breaker open. Let's zoom on that. And we can see here the TRV exactly the same as here. Alright? So what I'm gonna do is I'm gonna copy this device and put it directly to the to my design for each breaker. Okay, now I don't want the model data to be available, so I can zap it. Here it is. So this one will be the TRV of breaker 1. Of breaker 2, sorry. And this one will be the TRV of breaker 1. Okay, so now what I have to do is to put here as an input the state of the breaker. So to have the state of the breaker, it's very easy. You just go in the breaker itself and you go in observe. Then you can select the state of the breaker. So what we're going to do is we're just going to do it for the phase A, but you have to do it for every phase, obviously, for the TRV. So then now to have access to this state, as you can see, if I zoom, now I have here a small S, that means the state of this breaker is available. To have access to it, I just have to name the wire here S underscore and the name of the breaker. So I right click, go to name, I put it visible so that I know the name of this wire is important, and I call it S underscore breaker 1. It has to be the same name as this one. And I want the phase A, so I had A. All that is explained following here. It's explained in this text. Okay, and I do the same thing, I copy here for this one, but with this time the breaker 2, so I change the name. Okay, and so now I can put the here the scope. So we have TRV breaker 2. Here it's TRV delay breaker 2. And same thing for the breaker 1. So again, all that I can send it to you if you send me an email. I can send you those. Control that draw automatically the TRV, and they will be available. They will be available in the future version of EMTP. So here it's the TRV underscore D, the delayed. And the TRV itself. Okay, so let's run this simulation again, and this time we're going to compare the inherent TRV we find here with this network with the actual TRV that the breaker is supposed to withstand. Okay, so we open again scope view. We added some signals, so we have to reload the data source. And then we see now we have a new signal type named control signal. And we can find the scope we just added. So let's put on page 1 the one related to the breaker 1. Oops, sorry. So I click on it. They come here directly. I can remove the phase B and C. Even if when you do such a study you have to do that for the 3 phase. Here we do only it for the phase A because we don't have enough time, but it's the exact same thing. And on page 2 I put the one of the page 2. Okay, I think I did a mistake here. Oh, I forgot to select the observable. Sorry about that. I forgot to select the observable of this breaker. Okay, so I run the simulation again. It works fine with the first one, but the second I just forgot. Okay, it's better now. So see, as soon as the breaker open, we have here the envelope that the breaker, which has, according to the standard, which has a short circuit current interruption capability of 30,000 amp. Here is the envelope. Right, so if I zoom on it, so remember in that test we're interested in the worst overvoltage. We have a pretty good margin here, so it's fine for this side. Now let's have a look on the other side. So the other side, you know, the voltage can be positive, negative. So here it's negative, bad luck. So I'll have to put this value here negative if I want to compare. So I go back here and I just put a minus in front of the TRV so that I take the opposites of the value and I can compare. Let's unzoom a little bit and zoom here. So this time it's not good. We can see here the maximum value, it's too high, so that means this breaker cannot cut cannot withstand this TRV, and we're going to have restrike and reignition. So what does that mean is here we have to do something, either take a breaker with a higher short circuit current interruption capability, or we have to add capacitance to have a smaller TRV. It's also possible with EMTP with that now to simulate the reignition. So for that we can take the exact same block we had and compare this voltage with this one and use a control gap and close the control gap as soon as the voltage reaches the limit. So like that, it's kind of a cheap model, but a pretty good one to simulate the reignition. So if you want for more information about that, you can contact me as well. I can send you some model. And the best here is, of course, to model the arc, and in that case, it's the most precise. Okay, so very quickly, we won't do that together because we don't have time, but I will. The same way I built the rating TRV here, I built a same device that draw the prospective TRV calculated by the application guide. So let's have a look at it and see if it's close to the result that EMTP-RV gives. Here we go. So that's that. I built it before. I built it kind of the same way. We just build the one together. So it will draw the results of the end calculation made in the application guide. So let's draw it and call it TRV prospective. So it's just to show you that in the end the end calculation gives the same result as advanced software like EMTP, and it shows you also that the result that EMTP gives you are the one that you are supposed to find according to the standard. Okay, so I will do that only for the breaker 2 because we don't really have time to spend too much time on that. Okay, so if I open scope view again, here we have, so we can put it on page 2. So we can see it's actually pretty good. So it fits pretty well. The reflection in the waveform is it's more precise, obviously, with the EMTP. But see, we can see it comes in the same time as well as them. So it's actually pretty impressive. Okay, so now let's keep going and go through the short line fault. Okay, so this time the fault will be on this branch. It will be a fault at 3.2 kilometers. Okay, so let's change the name of it and call it now short line fault. Also, I'm gonna enlarge the sheet to have more space. So for that, I go in Options, Sheet Size Wizard, Auto Expand. Here it is. Okay, so the fault will be here. So what I'm gonna do is I'm gonna divide the line in two parts. One which is the short line part between the station and the fault, and one which is the rest of the line. And the fault will be between the two of them. Okay, so the fault is at 3.2 kilometer. Here it is. And so this one, in the end, what we have as a length, it's 16 minus 3.2. You can do some calculation like that if you put equal in front. Go. And we move the fault. We move the fault here. Okay, so this time for the prospective TRV, I built as well. I will do quickly exactly the same thing of what I've done before. So this time the TRV, according to the standard, we're going to have two types of it. One which is like a triangular, and one which is exponential plus cosinusoidal. So that's what I built here. So I'm just going to copy and paste it directly. Here. Okay. Okay, so this time the fault is not three phase anymore, but it's one phase, so it's an unbalanced fault, and the other phase are open. So we'll do the fault on the phase A. Okay, and so the breaker this time will operate. It will be the breaker that operates here. So the breaker that operates here, that's insulated in the end, this line, is the one that will see the worst TRV. There you go. So let's call it 3. Okay, so now the other breaker are not in this scenario. The other breaker will not see any TRV. So let's change the name of that to put now 3. Okay. It is so, and the prospective TRV here. So after I put a tracker, because here we are just interested in the rate of increase of the recovery current. So at the point I just put the maximum tracker, because the way I build that, it's valid only for at the beginning for the rate of increase. Okay, so let's call it a prospective TRV again. Oops, Here you go. Okay, so what we're gonna do, we're gonna open this breaker at 10 microseconds. The other breaker, it doesn't matter really because the other will open before, but let's set them never open. Okay, so now what happened here is like we have a very short line, so the propagation time here will be very fast, actually way more faster than before. So I have to decrease the time step, and we're expecting here a very high frequency phenomenon. But that's exactly in that kind of case where using a frequency dependent model of line will be very important. So I put a time step 10 times smaller, and I can do only a simulation at 20 milliseconds because it's really what happened right after we open the breaker that is interesting. Okay, so after in this case I will change the line and compare the result between CP and FD right after this case. But let's first run this one and look at the results. So see the simulation now, it's way slower because it's an extremely small time step. We are talking here of 100 microseconds, right? But it's the time for the light to go through that, and it's this time that will make the rate of it's this phenomenon of the short line that will make the rate of increase very bad. Okay, so let's go back and scope view. So I have to open scope view for this. I changed the name of the file, so I have to open a new scope view. Here it is. So I remove the signal before. So this time we look at breaker 3 phase A, and we compare with the TRV of breaker 3. Am I missing one? Okay, I forgot to name it breaker 3, but it's TRV breaker 3 here and TRV D breaker. Oh, I put this one already. And the prospective TRV. Okay, so let's put them all together. Here it is. So this time you see the magnitude is smaller of the overvoltage, but you will see the rate of increase is way worse. Oof, and it's actually very limit here. We go up to the TRV, so that means this breaker is definitely not the good application for this case, and we'll have to go to with a higher short circuit current interruption capability. But what is interesting here is look at the green curve. Maybe I zoomed a little bit too much. The green curve here and the red one. The green one is the one calculated by the prospective, by the application guide, and the red one is the one calculated by EMTP. So they are very close. So it's actually good. Okay, so now I'm gonna open the last two cases of this webinar. We are like a little bit late. So the last two cases, they will be the same case, but we will build the line differently with a frequency dependent model of line and a constant parameter of line, and we'll compare the results of those. Okay, so here are the case. I built them already to save some time, so I will just show you how to create the model of line. Okay, so to create that, what I use this time, and I go in the library line again, and I use this tool, the line data is the one here. So with this tool, the input data are the tower configuration. Okay, so if I open one, okay, if you need some help about that, like in every device in EMTP, you have a tab named help. Here you can have a look at it. So the way it works here, it's you have to specify the tower configuration. So first the number of conductor, 3 conductor plus plus the shield. Then the number, you can put more than one conductor per phase. So you are very free to do whatever you want. Then you put the DC resistance for the conductor, the ground, like the neutral here, and the phase, the outside diameters, and then the geometric organization. So for that you put a reference, and you put the horizontal distance to this reference and the vertical distance for this reference. Also you have to tell the vertical height at midspan. If you don't have this information, you can just put the same and the software will calculate a typical value for you. Okay, so you have a lot of options. You can put in metrics or not. You can consider a skin effect correction, so you can get very precise here. And so then you choose your model. So you have the frequency dependent model of line, which is very good for the line, or the CP, which is the same we used before, but you can also generate the CP like that. Okay, so for the line, the best model, the model we advise is the frequency dependent. For the cable, we do the same way. We advise you to use the wideband model, which is the best model for the cable. Then you put the line length and the ground resistivity. So here we put typical value. It's usually hard to find the ground resistivity. And you just have to go to save and run the case, check that, and click it. So when you click, the software will generate the case. The name was line 12_8km. If you go in the console, they will tell here that it has been successful. And so what you have to do then is just to go inside the line itself. So this line, it's the one, if you go in the library lines, is the frequency dependent line. It comes as a 3-phase version like that. Then you open it and you select the data file and you find the one you just built, which is this one, line 12_8kV_pen. And you say OK, and now your model is built automatically. You can put a 3-phase bundle like here. For that you just go in the drawing and you say 3-phase line type and you apply that change. So I did that for all of them in this simulation, and in that one I actually did the same but with the CP line. Okay, so let's have a look at the result. I ran those simulations already. As you've seen, they are a little bit long because the time step is very small. So to save some time, I built them already. So I load them to scope view. And I'm gonna superimpose the voltage of the breaker on the phase A again. There you go. So we can see the difference of the two lines. Okay, so first, that doesn't matter really, but the wideband one, not the wideband, the frequency dependent model of line is the red one, and the blue one is the CP model. So what we can see, this one closed a little bit before, but it's not a big thing, you know. It's just because to open the breaker has to wait a zero crossing, and so here there is a little bit difference in the model of line, so the zero crossing doesn't occur exactly at the same time. But what is interesting is see the rate of increase. It's not obvious here, but maybe if we zoom it will become more obvious. The rate of increase is slightly bigger. Oops, sorry. It's slightly bigger for the CP model, right? And also the magnitude is bigger for the CP model. So in the end, you are more pessimistic if you use the CP model than if you use the FD model. You can actually calculate the slope if you click on 2 points like that. Whoop. And you can see the value of the slope for this one and do the same for the other one and compare. And you see this one is maybe It was maybe 10% less than the first one. Okay, so it's just to show you. Also, you can see the damping in the end. That's interesting. Look at the blue curve, it's constant parameters. So the value of the resistance, for example, stay the same as the one at 60 Hz. There's almost no damping because the resistance increases with the frequency. Where with the frequency-dependent model of line, you can see this damping very well. So you can see how powerful this model is. They are very good model. Okay, so I think it's over for today for the TRV study. I really hope you enjoyed this presentation. If you have any question, we're going to stay connected for 15-20 minutes. So we're going to stay here to answer your question. Please do not hesitate. Also, we'll be happy to help you if you want more information in the future. You can contact us at the email written here on the screen. We'll be happy to help you or to share some model, the model you see during this webinar. We can send them to you, and we'll be happy to help you with that. Okay, so thank you very much. Have a good day, and enjoy your use of EMTP-RV. Bye.